Welcome! This tutorial will showcase how to prepare toolpaths for a terraced model in solid wood with descended building footprints. We will be using polylines for engraving that has been uploaded previously, but we'll need to upload the smooth model that we want to mill as a terraced one. So we'll click upload here, and Fusion 60 is a cloud-based program, so it uploads the file to Autodesk servers where it processes them, and then when the process is done, it is ready to be opened. This might take a while. Back in the saddle again. Alright, let's open this 3D model file. Having opened the 3D model file, we can insert the previously uploaded polyline document by right mouse clicking and insert into current design. Click OK to confirm. Now we can change workspaces from design to manufacture and create a new setup. First, make sure that the origin point is at the correct location, top of the stock, in the corner where both the X and the Y positive axes point along the edge of the stock and not out in the air. So this corner is correct. In the second tab, make sure to remove the stock side offset. It is advisable in Fusion 360 to change only the digits that you need to change. So in this case from 1mm to 0mm instead of deleting the whole field. Since if this value would have been anything else than 0, this unit would be equally important. The top offset can remain at 1mm. This 1mm top margin accommodates for any situation where the top surface of the material stock is not perfectly horizontal and planar. So as to make the stock height even, it might be advisable to add a little extra stock bottom offset, in this case 0.23, so that the stock height or the material stock thickness is approximately 61mm. These dimensions of the digital stock will also be the dimensions that you prepare your physical stock to, so take note of these. Click OK to confirm. Save the document with Ctrl S or the floppy disk icon, and the version description can be left at default user saved because this is not the name of the file but simply a description of the version saved. Okay. Now go to your preferred web browser and enter cnc.kthcnc.sc. It's simply a URL to a Google Drive. Here you have reference photos from previous CNC millings, and in the folder Fusion 360, which is the CAM software that we use, you can enter it. You have a data sheet that collects toolpath settings for operations from the last 7 semesters. And using the reference photos, all of which have indices attached to them, all of which are prefixed with the indices of the toolpaths, you can find the specific toolpath settings that were used for a reference that you like, or that is relevant for your project. In this case, for this tutorial scenario, we have already prepared reference data specific to this tutorial. So if we highlight the first one here, and you can scroll sideways by holding Shift and scrolling, we see that we have a 3D adaptive toolpath using the product ID of number 30. So now we can go back to Fusion 360 and we'll create a 3D adaptive clearing toolpath and we'll select number 30 as our tool. If you don't have the product ID column here, you can easily enable it here by clicking the cogwheel and entering product ID, and then you can just check this checkbox. And then you can optionally sort by product ID by clicking the header. Now we'll go down to number 30. This is a surface planar bit. It's important to note already at this stage that the reach, the length of the tool from tip of the tool to the bottom of the tool holder is fairly restricted. It's only 37mm. This means that as a safety measure, we should not allow this tool to go deeper than the length below the tool holder. So with a reach of 37mm, we might allow a maximum depth of 36mm. We can select this tool. As for the spindle speed and the cutting feed rate, let's go to the datasheet. And here we see that the spindle speed is set to 4000 RPM, so we'll change from 5000 to 4000. It is of utmost importance to only change the spindle speed and not the ramp spindle speed. The ramp spindle speed setting will be interpreted erroneously by the CNC machine, and instead of using this as the ramp spindle speed, it will ramp up the feed rate progressively, running amok and dashing into oblivion. So make absolutely sure to only change the spindle speed and not the ramp spindle speed. The cutting feed rates should be set to 4000 as well, so 4000 millimeters per minute. If you go to the datasheet and you scroll to the right by holding the shift key and scrolling, we see that we also have pull away active, 2mm shaft clearance and 5mm holder clearance. So we should activate shaft and holder and make sure that the mode is pull away, and then we should increase the shaft clearance to 2mm. This is a recommended standard safety measure, although redundant in this certain case due to the fact that this tool has a wider diameter flute than the shaft or the holder itself. Nevertheless, there is no disadvantage in activating it. Let's go to the second tab, Geometry. The machining boundary can be set to none, and we should have rest machining active. Rest machining means that succeeding toolpaths will take into account the volume that has already been removed by previous toolpaths, thus not cutting the same volume twice. If we go to the third tab, Heights, here it's important for this specific tool that had a reach of 37mm that we change the bottom height to be from the stock top and then have an offset of -36, 1mm less than the reach. This means that the tool will not progress any deeper than the value we have set here. Let's go to the fourth tab, Passes. If we go back to the datasheet, we see here that we have conventional milling set here, and that means that we should change from climb milling to conventional. Very briefly, conventional milling leads to less vibrations, although more rubbing, which is an acceptable trade-off when milling solid wood. The maximum roughing step down. In the datasheet, we can see the maximum depth of cut. It's 1.5mm, and there is no fine step down. So in Fury 60, when entering the roughing step down, that is the large increments in the vertical movement of the tool, and then you can optionally add fine step downs, which are the fine increments in between. In this case, so as to disable fine step down, we simply enter the same value as for the roughing step down. Flat error detection takes a very long time to generate, and we have no practical use for it in this toolpath, so let's disable it. The stock to leave here should be slightly increased. We want to leave sufficient material for the succeeding toolpath to properly define the final surface, without this toolpath chipping away too much. If we go to the datasheet, we can see here that we leave 1mm of radial and 1mm of axial stock to leave. So we'll change the first value here to 1. The second value is parametrically dependent upon the first, so we'll just leave them at 1. If we go back to the datasheet, for this specific tool, it is very important to change 3 settings in the linking tab, the 5th one here. And that is to change the ramping angle to 0.5 degrees, to change the helical ramp diameter to 70mm, and to change the minimum ramp diameter to 50mm. This is due to the fact that the tool that we use has a stiff part with no flutes in the center of the tool on the bottom, and this stiff part is receded approximately 2mm from the tip of the tool, and so as to make sure when doing helical ramping movement not to leave an unmilled pillar of material under the center of the tool, we need to force the tool to make sufficiently large ramping maneuvers when needing to do so. If we go back to the datasheet, we see here that we have changed every relevant setting, so we can simply click OK to generate. And Fury 60 often jumps to the background, so to say, so let's Alt-Tab back, and that was quick. We see here that this toolpath is simulated to take 1 hour and 20 minutes. It's very important to note that the simulated time will never be the actual milling time. Statistically, different types of toolpaths have different time deviation factors. And if we open Rhino and Grasshopper, there is a definition that we can use that makes it easier to calculate the total expected max time it takes to mill for several toolpaths. So let's open Rhino and Grasshopper, and here we have it. This definition can be downloaded by going to your preferred web browser and then go into gh, as in grasshopper.kthcnc.se. And then you can go to definitions, and you can go to fabrication, and here you have estimate CNC toolpath time. And here you have the definition itself, as well as an image preview. Here we should enter 1 hour and 20 minutes, the simulated time of the first toolpath. It was a 3D adaptive clearing toolpath, and that gives us an estimated reasonable max time for the toolpath of 2 hours and 24 minutes. This is less than half than 6 hours, the maximum total toolpath time, and it is a good idea to make sure that there is adequate time for the toolpath that actually is going to define the final surface. So with this we can proceed. If we go to the datasheet, we find that the next toolpath that will define the final surface is a 3D adaptive one. and it uses the tool with product ID 19. So let's go back and let's create another 3D adaptive clearing one. Let's select tool product ID 19 from the previously imported tool library. Here we have it. It is very long, it has a very generous length of the flute and a very generous range. It has a length below the tool holder of 125 millimeters. That's more than sufficient for any model. And this specific model had a stock of 61 millimeter material thickness, easily accommodated by the range of this tool. So let's select it, and then we can check the datasheet for spindle speed and cutting feed rates. So here we have 8000 as the suggested spindle speed, and as for the cutting feed rate, 1500. We should enable shaft and holder. If we check the datasheet and scroll with shift and the scroll wheel to the right, we see that we have 2mm shaft and 5mm holder. So let's change the 1mm shaft clearance to 2mm. Very good. As for the geometry, we have no machining boundary and we should have a rest machining active. Very good. The toolpath, due to rest machining being active, will use as the source the result from the previous operation as its starting point. Very good. In the heights, we don't need to change anything because the tool that we have used has sufficient reach. In the passes tab, let's change from climb milling to conventional as we did previously, and let's check the suggested maximum roughing step down. So we'll go back to the datasheet and we'll scroll back here. 4 millimeters of maximum depth of cut. So 4 millimeters of maximum roughing step down. Let's check what fine step down is suggested. It is suggested a 2 millimeter fine step down. So we'll do a fine step down of 2 millimeters. We'll disable flat tire detection, consistent with the reference here. We should have no stock to leave disabling this, because this toolpath will define the final terraced surface in final fine steps of 2 millimeter. We will have to verify the time it takes to mill. If it takes an excessive amount of time to mill with 2 millimeter fine step down, we will have to increase the fine step down, unless we want to go back to Rhino and reduce the size of the model, either by further restraining the crop or selecting a smaller scale. We can go back to the datasheet and we see here that we have no other relevant settings to change, so we can simply click OK to generate. And Alt-Tab back. We see here that the simulated time for this toolpath is 1 hour and 49 minutes. Let's go to the Grasshopper definition and input 1 hour and 49 minutes. And it is a free adaptive toolpath. And that takes 3 hours and 17 minutes, which yields a total of 5 hours and 41 minutes. As such, this is still under the maximum of 6 hours. Let's see how long the next toolpath takes. Let us go to the datasheet and we'll select the third toolpath here. It's a 3D pocket toolpath and it uses the same tool, product ID 19. So we'll use 3D and 3D pocket clearing. As default, the tool of the previous toolpath is automatically selected, so we can keep it. And as for the settings of the spindle speed and cutting feed rate, we might want to adjust this slightly due to the fact that we move in more constrained spaces. So let's see here, the same spindle rotational speed, but with slightly less feed rate, slightly slower in feed rates. So 8000 as spindle speed and 1250 as cutting feed rates. Let's enable shaft and holder with pull away and increase the shaft clearance to 2 millimeters. In the second tab, Geometry, it's important to change the machining boundary to a selection of the actual pocket faces that we want to mill. So let's go to Top View and select these descended building footprints. With all of these building footprints selected, their faces, we have to make sure that the tool containment is tool inside the boundary. We don't want it to escape outside of the building footprints, and the additional offset should be set to 0. Rest machining should be kept as active because that reduces the time of this toolpath due to the fact that the previous toolpath has already done some of the work. Let's check the datasheet. If we scroll here with shift and the scroll wheel to the right, we see that we have a maximum depth of cut of 2 millimeters. And no stock to leave, conventional. We can go back to Fusion 360. In the heights tab, we don't need to change anything. In the passes tab, we want to change the direction to conventional and the smoothing deviation to 0.75. The maximum roughing step down can be set to 2 millimeters. And then for this specific toolpath, we want to keep flat tire detection on. We want the final depth to be the depth of the actual surface. We should disable stock to leave, not leaving any margin. In the linking tab, the fifth one, we don't need to change anything, so we can simply click OK to generate. Let's Alt-Tab back. And let's click the home icon here to reset the view. It says here that the simulated time is 22 minutes. Let's input that here. And we see we're going to exceed this. 22 minutes. We don't have enough data for the 3D Pocket ones to have a statistically reasonable max time factor. We'll choose 3D Adaptive here anyway. And we see we have 6 hours and 20 minutes. We should try to make sure that this is less than 6 hours. So let's go back to View 360. And then perhaps we can actually adjust the settings of the 3D Pocket one to be slightly more aggressive in two ways. We can increase the cutting feed rate back to the 1500 that was used for the previous one. There might be an increased risk of chipping along the edges, but we want to see if we can significantly reduce the time it takes to mill. And we can also go to the fourth tab, passes, and here we had a roughing step down of a maximum of 2 millimeters. We used 4 millimeters for the previous one as a maximum roughing step down, so let's double it, 4 millimeters. This should still be reasonable, but since it increases the load of the tool and the risk of the tool being deflected by the forces it engages with, it might lead to chipping or a deteriorated surface. We'll accept that trade-off as of now. Click OK to regenerate, and Alt-Tab to go back here. Did it somehow take longer now? If we go back to Rhino and Grasshopper, previously it took 22 minutes and now it's stated to take 26 minutes. It might be due to the fact that now with an increased step down, it traverses more between these different areas. So let's see if we can change that. If we go to the fourth tab, passes, and we'll reset the maximum roughing step down to 2 millimeters while still keeping the 1500 millimeters per minute adjustment for the cutting feed rates. We can click OK to generate. Now we are down at approximately 18 or 19 minutes of simulated time. If we are a little generous and go down to 18 here, now we are at less than a quarter, surpassing 6 hours. One could say that this simply does not cut it. However, 15 minutes of overtime might not be seen as too critical. Let's see if we add the two last toolpaths, the 2D trace operation for the polylines to be engraved. The polylines, as they have been previously uploaded, they have also been used for engraving toolpaths in a separate document. So we'll actually do like this. We can open the previous document by double-clicking on it, and then we can simply select with Control, multiple selection, and then right mouse button click and copy this, and then go to our active document, and then right mouse button clicking the setup one here and pasting. Now we can close the previous document, and you find the 2D trace operation in the 2D sub-tab, 2D trace. For this scenario, we are simply going to double click this to open the settings for the toolpath. We're going to go to the first tab, and we make sure that we have a correct tool here, a 12mm flat end mill designated to tool holder 5. We can select here, and we can simply see here that we have product ID number 1. Is this corroborated by the datasheet? Yes. The succeeding trace operation has tool product ID number 1 as index. Then we can click cancel, and the spindle speed is set to 7000, the cutting feed rate 1250, the maximum depth of cut 1 millimeter, here interpreted as the axial offset from the projected curve to the milled depth. It might actually be that the reference is from a smooth model, and with a terraced model you always have to account for the height of the terrace steps as well, 2 millimeters in this case. So the maximum depth of cut might actually be 3 millimeters here. We'll have to check that. Here we have an axial offset of -1. Let's see if we go back here. We can go to the Geometry tab, and then we can delete the previous curve selections. Those reside in the previous document. And then we should expand the models, expand this document, expand the referenced or inserted document, expand the sketches of that document, and here we see the two different layers. So this specific toolpath is for the roads. So let's select the roads. And then in the third tab, we don't need to change anything. In the fourth tab, we make sure that the axial offset is set to -1 millimeter. And sideways compensation is center and no chamfer. It doesn't even appear for this specific selection set. Okay. And if we simulate this and jump to the end of the toolpath and hide the models, we see here that we have 1 millimeter below the surface when the terrace step is as close as it gets to the actual surface. But then of course the terrace steps of 2 millimeters is also added. So we actually get 3 millimeters of depth of cut. With this tool at 12mm flat end mill, that is of no problem at all. One could reduce perhaps to 0.5 mm there. Let's do so. So let's click X simulation, and then we can double click on this. And then we can, in the fourth tab, passes, reduce the axial offset to negative 0.5. And then we can generate, and we can simulate, and we can go to end of toolpath, and we see that now it is slightly reduced here. Still looks good, perhaps even better. Let's keep it like this. Here we see a warning sign that the previous toolpath, or actually the first toolpath, might actually leave too little of margin for the second toolpath to properly define the final surface. Let's click X simulation, and let's simulate this second toolpath intended to define the final surface. Here we see before, and then we go to end of toolpath. Yes, we see that the first toolpath, it leaves an insufficient axial margin for this tool to actually properly define it. As such, we should exit the simulation and redefine the stock to leave for the first one. In hindsight, it is quite clear, because if we go to passes and we see here that we leave an axial stock to leave of only 1mm, while the toolpath that defines the final surface has a fine step down of 2mm. The radial stock to leave can still be 1mm, but the axial stock to leave should be 2mm. And we can click OK. This will of course change the circumstances regarding the time it takes to mill for this and the succeeding one. Let's see here, this takes 1 hour and 17 minutes. 1 hour and 17 minutes. And then if we simply regenerate either with Ctrl G or generate, now we have 1 hour and 56 minutes here. So 1 hour and 56 minutes. We slightly reduced the first one and we slightly increased the time of the second one. And then we'll see for the pocket. So let's just Ctrl G to regenerate. 19 minutes. And we'll see here that the new time is 6 hours and 22 minutes. As such, perhaps we should have, instead of 2mm, 2.5mm between the terrace steps here. So in hindsight, we need to change the passes here, and we'll leave 2.5mm of axial stock to leave, and click OK to regenerate. This now takes 1 hour and 17 minutes of simulated time, the same as previous. And then as for this, we can simply double click the icon here to open the settings for it. We can go to passes, and then since the fine step down will be 2.5mm, it would be great if the maximum roughing step down was divisible by 2.5. So it would be great if it was 5. 5mm of step down in solid wood is too much. So perhaps we keep the fine step down at 2 and the maximum roughing step down at 4, but we'll slightly increase the cutting feed rate from 1500 to 1750. And we aim to keep the feed per tooth at approximately 0.094. So we increase this to 1750, and then we also adjust the spindle speed, perhaps up to 8500, perhaps 9000 here. Yes, and now we are down at 97, which is not equal to 94, but it's still close enough. So now we have increased the cutting feed rate, the rate at which we cut the material, while also compensating for the increase in feed per tooth that yields by also increasing the spindle speed a little. One may make these small adjustments in feed rate and spindle speed at the expense of increasing the risk for excessive chipping. It might be more advisable to simply go back to Rhino and reduce the size of the model slightly. In this case, we'll allow these adjustments and we'll click OK. This toolpath has a simulated time of 1 hour and 43 minutes. 1 hour and 43 minutes. Let's generate the pocket one as well, Ctrl G. It needs to be regenerated due to it having rest machining active and relying on the previous operation as the outset for this one. And we have 19 minutes as we previously had. And we can see without the trace operations, we now have 1 minute shorter than 6 hours. That is most reasonable and very good. With the addition of the trace operations, this might be a couple of minutes more than 6 hours expected max time, but that is still totally reasonable. Alright, let's progress. So the trace operation here, we don't need to regenerate it since it does not have rest machining active. The sixth one we have not yet redefined. So let's see here, if we go to the datasheet, and if we select this here, we should make sure that it has the correct tool, number 27, and here we see that it has number 27, product ID. and 12,000 as spindle speed, and 1,000 as cutting feed rate. Very good. If we go to the geometry, we can delete these selections of the previous document, and then we can select the property line. And heights should not be adjusted. The passes we see here, we have, since we copied this toolpath, we have a setting here that is already preset as negative 0.3 millimeter. That yields, with a 45-degree V-bit with 90-degree total angle, it yields 0.6 millimeter of width of the groove. That's recommendable. No stock to leave and no settings in linking changed. Then we can simply click OK to generate. And this takes 1 minute. So the first trace operation takes 1 minute and the second takes 1 minute. So we'll add 1 minute each here for the 4th and the 5th. And make sure that these are set to the operations, because they deviate far less than the 3D adaptive one. And now we have 6 hours and 1 minute of expected max time. Very, very good. Let's see here, because due to the very same fact that the previous trace operation had, that the 2 millimeter height of the terrace steps, it also contributes to the depth of the trace here. So let's simulate this and see if we have a lot of collisions. We have a lot of collisions. That means, because this would be a critical collision, for this specific tool, we only have sharp flutes down here and none here at a smooth shank. So this would be a critical collision. Since it's a solid wood material, it would simply lead to, in best cases, that the router bit itself shatters. In a worse scenario, it would lead to damaging the tool holder or the said axis of the CNC. So this is not acceptable. As I analyze the situation, we will not be able to use this specific tool for this specific model, because even though we could reduce the axial offset to the point that we actually are not even cutting in the model, so as to make sure that we do not collide here, that would not be a really good option. So we can exit simulation here, and then let's see here what tool holder we have free or at disposal. We have tool holder 1, but that's 16 millimeter. Tool holder 2, tool holder 4 is still free, and tool holder 4 is the 6 millimeter shaft one. So we can exchange this tool to one that is 6 millimeters. So let's go to the imported tool library for the large CNC machine, and then we can go down to, I think it is 29. 29 should be sufficient. It's a very short tool, only 50 millimeters below the holder, but I think that this will be unproblematic. We'll select this, and then we'll adjust the spindle speed. I think 12,000 might be good also for this one. 12,000, and the cutting feed rate as 1,000. And when changing the tool, all of the tool specific settings are reset and should be readjusted, but we don't need to adjust these anymore. Perhaps if we want to adjust the axial offset, if we would do, no, let's not do 0, let's do 0.3. Now we don't have the V bit, the angled bit anymore, so this axial offset is not relating anymore to the width of the groove. The width of the groove will always be 6 millimeters with this tool. So let's see here, if we do negative 0.5 and click OK here, and then if we simulate this, we have no collisions, whereas we previously had lots of collisions. If we simulate this just to make sure, or we can actually just go past to the end of the toolpath at this stage. While perhaps not optimal to use a 6 millimeter, which is fairly wide in this scale, it is half the width of the road that we do here. It might look more like a bicycle lane than a representation of a property line, but we'll have to be satisfied with this with the certain circumstances that we have here. The terraced model contributing to too high of a difference between the original surface and the terrace steps to be accommodated by the V-bit, and thus we changed to the 6 millimeter flat end mill, and this result is what we get. We can exit simulation, and now showing the models again. We have 1, 2, 3, 4, 5 toolpaths, and all of them are verified to be reasonable in the time it takes to mill, with regards to the time factor and the maximum expected time it takes to mill. As such, we should also make sure that all of the toolpaths are safe to run. That is, that there are no critical collisions. So let's verify the collisions. So select the first of the toolpaths, go to Actions and Simulate. And we have at least one error here we see. If we go to the second tab, we see that we have 6 registered collisions. We can go to Information and Issues, and we see these 1, 2, 3, 4, 5, 6 collisions. If we click on the first one here, we can see where the collision is registered. It was really easy to see that this is registered as a collision between the stock and the shoulder of the tool. However, the representation of this tool in the tool library is not 100% accurate due to the fact that the exterior of the tool has 100% sharp flutes, although the interior of the tool, underneath the center of the shaft, there is a significant area that has no sharp flutes at all. That stiff or smooth area is receded a little more than 1.5 millimeters from the tip of the tool, so thus the tool itself here has been chosen to be represented by sharp flutes only where it actually has 100% cutting capacity. In reality, all of the exterior have cutting capacity, but not underneath the center, in the middle. So this is registered as a collision, but it is verified visually to not be a critical one, since it is colliding between the exterior, which actually has sharp flutes, and not a theoretical smooth shoulder. We can move to the next one, and here we have a similar scenario, not a critical one. For the third one, here it is not evident exactly what is colliding, so we can zoom out here by scrolling, and then we can zoom in at the present collision, and then we can move backwards a little. And here we see it. Yes, that's non-critical, definitely. And I think that was the third. So let's do the fourth now. And it's in the same area as previous. That's not a critical one, because this will be engaged with the sharp flutes of the exterior here. And then we'll do the fifth one, and it's also here. So my assumption would be that if we zoom in here and go slightly to the left, we will see that there is a small, yes, exactly, it was that one. And then we should do the sixth and final one, and it is here. I don't see exactly where it would register, but if we go outside here by scrolling and then inside, closer here, and then going backwards by a little, we should see what it collides with. Yes, this small pillar there. That's not problematic at all. Alright, so we had 6 registered collisions and we visually verified that none of them were critical. Close. We can exit this one, and then we should simulate the next one. Let's go to the info tab here and wait for the verification of collisions. There were none. Very good. We can exit simulation. We can go to the pocket one. We'll simulate this. We'll go to the info tab. We have one collision and we have it right here. We could either click here in the timeline, or we could go to information, issues, and click here. And it registers a collision where it moves rapidly into the stock, but we see that it is a so small amount of material that it engages with during the vertical descent, the plunge, that that's not problematic at all. Okay, close and exit. And as for the trace operations, they should be visually verified, the whole of the toolpath visually yourself. With this tool, the very long one, it might be a given fact that this will not collide with anything because it is so massive in length. But we'll still need to verify this as it moves here. It does not unexpectedly come into contact with such a steep cliff that it will go all the way up to the tool holder. We can increase the speed here of the playback. Hide the models. Alright, looks good. And there were no formally registered collisions either. Let's visually confirm that there are no collisions for the 5th and final toolpath. In the info tab we see that there are no registered collisions, and if we play back here with slightly slower playback speed, we see that it enters the material like that. It is not at risk of colliding with the tool holder at all here. Very good. Here we see there is actually an insufficient depth so as to make the toolpath actually making a mark on all of it. So we can set the axial offset slightly lower. So we were at 0.5, we can perhaps do 0.8. Okay. And then we can simulate. And then we saw it happen before. We might do it again at a slightly higher playback speed. And let's see how it looks here. Yes, it has already passed. Oh, actually it does here, but this was much less discernible than the previous one. Yes, and it did not collide anywhere. Very good. We can exit simulation. And now, having both made sure that all of the toolpaths are reasonable to mill in the expected maximum time it takes to mill, as well as there being no critical collisions registered to any of the toolpaths, we are now ready to post-process the toolpaths. Although it is possible to post-process all of the toolpaths in one combined toolpath, it is advisable not to do so, simply due to the fact that the CNC machine, not very regularly, but perhaps once every 2 or 3 weeks, it freezes up during operation. And during such a freeze up, one needs to either restart a toolpath or manually split the toolpath. And in either case, it's much better if these toolpaths are individually post-processed. So select the first one, go to Actions and Post-Process. Make sure that the post-processor that you select, you can choose it from library where you have previously imported them, is the one that is relevant to the machine you're using. And make sure not to click this button to update the post-processors, because the updated generic ones will overwrite custom changes made to the slightly older ones. You can select this one, then make sure that the output folder is a folder where you know how to navigate to. And as for the name, it is quite strict with the syntax or formatting, simply due to the fact that the CNC controller will not accept a file that has any special characters, any spaces, any periods, or any other punctuation symbols. The graphics user interface is also very restricted and only shows the first 12.5 characters. So it's important to be concise and to name your post-process toolpaths accordingly. The date of your scheduled CNC milling in a big endian style, so 24/06/14 underscore the order of the toolpath, so in this case the first toolpath, and then underscore tool 3 in this case, since we're using tool holder 3, and then you can use underscore and add a suffix, perhaps Norrbyskogen underscore building footprints underscore terraced model, and we'll add alder wood there as well. Make sure to select this either by clicking and dragging or Ctrl A and copy with Ctrl C. That makes it much easier for you when you progress with post-processing the other toolpaths. Now you can click post, and here you see that the code has been successfully posted in the directory you chose. Very good. And then you can select the next one, go to Actions and Post-Process, and then you can simply Ctrl V to paste, change the order from 1 to 2, since this is the second toolpath, from tool holder 3 to tool holder 2, and then you can just post. Very good, successfully posted. Move on to the third, and post-process, and then Ctrl V to paste, and this is the third toolpath, and this is still tool holder 2, and then you can post, and this is successfully posted. Very good. And then you can move on to the fourth one, and Actions and Post-Process, and Ctrl V, and this is the fourth one, and this is using tool holder number 5, and we can post, and it is successfully posted, and we can move on to the fifth and final one, and Post-Process, and Ctrl V, and let's change this to the fifth one, and we use tool holder 4. Very good. And post. And now all of these 5 toolpaths have been successfully posted. Very good. One final thing to do that makes it easy to download the toolpath files on the computer that is connected to the CNC machine is to upload the toolpath files to a temporary folder in the Google Drive. So go to your preferred web browser and open a new tab and cnc.kthcnc.se. It's a URL to a Google Drive. And then you can open the temporary storage folder, and then you can create a new folder, and then you can name it with your name or anything significant. And in that folder, you can simply click and drag to upload those toolpath files. That makes it really easy to download on the computer that is connected to the CNC machine. Now, although you are done with the preparations of the digital toolpaths, we can still go back to Fusion 360 and showcase how to get a proper 3D model from the simulated stock. If you select the whole setup, and then you go to Actions and Simulate, and then you go to End of Toolpath, and wait for it to progress, and you can hide the models, and then you can right mouse and click on the stock itself, and go to Stock, and Save Stock, and then you can save it to a suitable folder, and then you can navigate to it, and then you can simply click and drag it into the Rhino document where you have your original file, and import a file with default STL import settings, and then you can move it, perhaps 450 in this case. And then if we change the display mode to Arctic, and then we can see a clear representation of how the simulated stock looks like after the 5 toolpaths. Very good. Now your focus may be shifted to preparing the physical stock, matching the dimensions of the digital setup stock in Fusion 360. Thank you for your time.